Isaac Newton's universal law of gravitation represents a quantum leap in human understanding of the forces that define the universe. Newton published this law in the late 17th century. He asserted that all objects attract one another and that this force, gravity, was responsible for holding the planets in their orbit around the sun. He had discovered the force that holds the universe together. Newton's force of gravity acted upon any object with mass, but not on massless entities like light. 200 years later, another great mind was pondering gravity. In October of 1907, Albert Einstein was working as a patent clerk in Bern, Switzerland. Between patent assessments, he was thinking about gravity and the fact that weight disappears during the acceleration of free fall. Jump off of a tall building and your weight disappears. You do not feel the pull of gravity on your body. You have become weightless. Where did the weight go? Or to rephrase the question, where did gravity go? Einstein's suspicion was that gravity had become something else. He believed it had become acceleration. Gravity and acceleration were equivalent. Later on, Einstein would recall this thought as being the happiest thought of his life. Einstein was so confident of his idea, he declared that an observer in a windowless room would be unable to determine whether his weight was being created by the pull of gravity or the force of acceleration. This assertion had some profound implications for the existing view of gravity. Consider this. An observer watching a light beam in a dark, motionless room, not affected by a gravitational field, would see the beam move in a straight line across the room. If the room started to accelerate, the observer would feel force similar to gravity, and he would perceive the light beam as bending. If Einstein was right, that is, gravity and acceleration are equivalent, then an observer in a gravitational field should feel the force of gravity and see the light beam curve, meaning that light, which is without mass, can be deflected by a gravitational field. This had significant implications for Newton's model of the universe. Einstein called this idea the equivalence principle. Proving this principle turned out to be difficult. The force of gravity in a laboratory setting is small. Einstein turned to a larger laboratory, the universe. If light from a distant star passed close to the sun, and Einstein was right, the starlight should be deflected by the powerful gravitational field of the sun. The problem, of course, is that you can't actually see any stars during daytime. They are lost in the glare of the sun. British astronomer Arthur Eddington offered a solution. He proposed to undertake this experiment during a total solar eclipse. With the sun blocked by the moon, stars become visible. Eddington organized an expedition to view the eclipse of May 29, 1919. Equipment was set up off the west coast of Africa on the island of Principe, and at Sobral in Brazil. Images captured during the eclipse showed a predicted shift in stars close to the sun. This was the evidence Einstein was looking for. Light, without mass, had curved in a gravitational field. A new model for the universe was confirmed. Newton's three-dimensional universe, defined by his law of universal gravitation, was replaced by an undulating four-dimensional landscape. Time and space shifting and warping, creating the illusion of force between objects. My mind struggles to visualize Einstein's creation. The geometry of space and time is complicated. Our current model of the universe represents knowledge that has been evolving from the first civilizations. A procession of great minds have brought us to this level of understanding. And a new generation of great minds is already proposing exciting possibilities for our next model of the universe. How wonderful to be living at a time when the internet makes it so easy to follow this evolving quest. For more science and technology videos, visit our website, hylaroad.com.